All righty, good morning, everyone. Show up eventually. So, just kind of remind what we talked about last time. So, last time we started chapter 18. So, we started looking at electrodynamics. And what we said is that as charges move through a wire, if we count the number of charges which move through a cross-sectional area, then the average current is equal to the change in charge divided by the change in time. So, the number of charges which pass through this particular cross-sectional area. So that's that guy. Say my cross-section area. This thing then has resistance and Ohm's law. So Ohm's law says that the potential difference that we apply across it, this is W, which most of the time we're just going to call is equal to the current times the resistance, where the resistance is equal to the resistivity times the length of the wire divided by its cross-sectional area. Then as the charges go through, again, they're making collisions with the atoms inside of here, causing the atoms then to start to vibrate more, which then causes energy to be lost, typically under thermal radiation. So in this case, the power which is lost is either equal to, in this case, it's going to be the current times the potential, or the current squared times the resistance, or the potential squared divided by the resistance. So okay, the first one is good for any type of electrical system, and then the second two are only for resistors. So, having said that, three of me. So let's start off with a group assignment. So I guess all of you are a group. That would be great. So I got two for you to start off with this morning. The first one here is mostly just playing with the definition of currents. And kind of doing it that way with some reminders of conservation of energy. See that here in a second. Talk about that one first, and then we'll talk about the other one. So this one says we have a steady beam of alpha particles, which are simply 2 protons. So the charge then is equal to twice the fundamental charge, traveling with a constant kinetic energy of 20 MeV. So what's an MeV? So an MeV is a mega MeV, where an EV is simply the energy it takes to accelerate an electron through a 1-volt potential. This is the definition of an EV. So an EV is exactly what it sounds like. So it's simply the charge of an electron times 1 volt. So if I wrote an EV in terms of other things, this would be 1.602 10 to the minus 19 coulombs times a 1-volt potential, which then would be equal to simply 1.602 times 10 to the minus 19 joules. So every electron volt for an EV is 1.602 times 10 to the minus 19 joules. So a mega is just 10 to the positive 6th. So anytime I have, for example, a mega electron volt, that's equal to 1 times 10 to the positive 6 electron volts. So an electron volt is just a unit of energy. So again, it's the amount of energy it takes to accelerate an electron through a 1-volt potential. Or this is the energy that the electron would receive being accelerated through a 1-volt potential. Anyways, and this carries a current of 0.26 microamps. So basically what it says then is that if our beam is directed perpendicular to some sort of flat surface, how many alpha particles strike the surface in an amount of time of 3 seconds? So let's say here is our beam. So here's our beam of alpha particles, where this is concentrating current, where the current is 0.26 microamps. So this is my current. What this is saying is it's hitting some sort of flat surface. So here's my flat surface, and that's then going to deposit alpha particles onto the flat surface. So basically, I am putting alpha particles into this. So it just simply wants to know then how many alpha particles are going to be in this particular region as you're here in the time span of 3 seconds. So here delta T is simply equal to 3 seconds. Part B then says at any instant, how many alpha particles are there in a given 20 centimeter length of beam? So now we're just saying that this is our length of beam, let's call that L, where L here is equal to 20 centimeters. And what I want to know again is how many alpha particles are inside of this section. I want to know what is n alpha. So how many alpha particles do I have inside here? Last thing is, then it says, through what potential difference is it necessary to accelerate each alpha particle from rest to bring it up to 20 MeV? So this is just conservation of energy, which we had on the last exam, which again says that energy plus the change in potential energy must be equal to 0 in this case, because I have no non-conservative forces acting in my system. Or this is the change in kinetic energy plus then the charge times then the change in voltage. Potential difference must then be equal to 0. So this is all you're doing for part C. Just to remind you, these things still exist. So that's it. So that's it for this one. So like I said, so basically all you're doing in this problem is playing with the definition of currents, and then in the first case, you know what delta T is. So here, all you're going to say then is that the change in charge is equal to the number of charges times the charge of each charge. Because if each one has exactly the same amount of charge, then I know the total change in charge is simply equal to the number times the charge. And we're told in this problem, the charge is simply equal to twice the fundamental. Great, that's pretty much it. Part B, then you're just playing with the definition of time. So rewrite time in terms of velocity and length and things like this. So you're moving at constant speed because it has a constant kinetic energy. Okay, so I'll give you a little bit of time to work on that, and then we'll switch to the next one. You're about to talk.
So when you do the MEV part, I think I did it, but then I don't know how to do it with the
I didn't hear about it.
Like, okay, so I think I solved it, but then, like, I still have MEV at the top, so, can I, like, I'm just trying to figure out how to, like, get it.
Right. So when you divide by the E, it just cancels out the
Right.
E parts. So then it becomes megavolts.
Okay.
But then you have megavolts.
So then I'll just go from this.
Well, you want a number, so there should be dimensionless. So let's see what you did.
That's true.
So what did you say? So you said.
So I thought I found delta Q.
Oh, okay. So you're on the right track. So the only thing is you're saying that you have an energy is equal to a current. Right? So not quite what we want, right? We want current is equal to a current. So what you want to say is that the current is equal to the change in charge over the change in time. Right? So basically you just want to replace that number with the 0.26 micro amps instead. Good. And now everything you did from there is still fine. So now you're going to take that 0.26 micro amps and multiply that by time. That time is just 3 seconds. change your units there. So now we have what, a core now, right? Okay. And then you know that it's delta n is equal to the number times the charge. And now all you want to do is take that and divide by the charge, which is twice the amount of charge. Okay. So you have the right idea. Just using that one wrong number. So, but other than that, no, you have exactly the right idea. Good.
Oh, okay, so 0.26. Okay, yeah. Okay, I got what you're saying. Yeah. Without saying it sometimes. Yeah. It was 2 times.
Okay, go on.
Yeah, I'm just reading through what we got. So.
Sure. No problem. How you doing, Josh? Well, yeah, that would be 0.26 times 10 to the minus 6. Because it's a micro. Because it has the units of amps, not microamps. And the mass that's on the bottom there is the mass of the alpha particle. Okay, so part B, you're basically going to do exactly the same thing, except now you want to rewrite delta t in terms of the velocity. Okay. Right? Because you know the length, so you're basically going to use the second kinematic equation to rewrite the velocity in terms of length and time. And then solve for the time. And then replace that delta t in the bottom of the same expression that you used. So I is equal to delta q over delta t. So you basically just rewriting delta t in terms of V and L. But you don't know V, which what you do know is the kinetic energy. So you can find V in terms of the kinetic energy. It's basically the same thing, just one extra step.
So changing the time would then be changing and you know change because they get to do sometimes they use it for lots of things just work on and then you solve because they do so you solve for the velocity and you plug that back into the equation. And so here you know all the you just have to make the energy physics.
In the end.
So you just have to convert it to the joules.
What's that?
That's what the solution. It's okay. See you.
Very good.
Just
one thing to note about EV, if I take an EV and I divide by the charge, where the charge is, say, the fundamental charge, the E's then will just cancel, so this then just becomes simply a volt. So that's one nice thing about using EV, because that stands for the charge of an electron. Then you divide by the charge of an electron, it just simply becomes a volt. Okay, go ahead.
So it's like the angels use the conservation. But like converted to joules, and then you bring up the potential energy into the Q times the change in the potential, and then you just solve for change. Okay. So it should be 10 megavolts.
Yeah. You're taking 20 mega electron volts and dividing by 2 E. So the E's will cancel, gives you just 10 megavolts. Or you can do a bunch of conversions and then get there. All right, so let's talk about the next one. Get a little bit started on that one. Save a little bit of time to talk about some new stuff today. So this one says that we have the filament of a light bulb is made out of tungsten wire, which has a resistivity of 5.6 times 10 to the minus 8 ohm meters. And this is in the form of a cylinder. So this is our cylinder, which has a radius of 5 times 10 to the minus 5 meters and a resistance of 200 ohms and a length of L. So this is my radius across here. This is my length. And then this thing has, again, a total resistance of 200 ohms. So it's a light bulb that is connected to a battery where the pretty big battery has a voltage of 120 volts, as is shown here. So then it wants you to determine all of the following things. So first, what is the length of the wire? And then what is the magnitude of the electric field inside of the wire? And then the number of electrons per second that pass through this cross-sectional area. So number of electrons per second is simply the current. So I just want you to find the current. Well, actually, that's quite true. So electrons per second is the current. So the number would then be the current divided by the charge of the electron. And then it wants to know what's the power dissipated by the wire. And then finally, the electric bill amount if the wire or if the light bulb is left on 24 hours a day for 1 month. And here, the electric company is going to charge you 15 cents per kilowatt hour. So one thing to note about kilowatt hour is, remember, watts is a unit of power, which is an energy per second or an energy per time. And then if I multiply that by an hour, that just makes it simply an energy. So basically, it just wants to know, so the electric company is charging you for the amount of energy that you're actually using. So if you leave this guy on for 24 hours a day for 30 days straight, so we're going to go with a month is equal to 30 days, how much money are you going to be charged by the electric company if they charge you 15 cents per kilowatt hour? So these are all things we're going to find out. And yes, I raised all the useful language. I can write that back up there if you want. Good job. Hardening or just using the definition of resistance. B goes back to what we did in the last section. That's a relationship between E and V. So going back to the E, delta V over delta X. Somebody passed out on that. Okay. Music is the next. Oh, the length of the way. You sure? It's good, small. That's it. So you took 200 times. Right. And then you divide it by 5.6. Oh, okay. I see. When you divide it here, you actually need to put correct. The reason for that is it's dividing by 5.6 and then multiplying by 10 to the minus 8. Okay, so without that parentheses there, so when you put the parentheses, it says you multiply by all of that. So that's why you're minus 16 there. It's kind of weird. That's right. It's an unfortunate thing with the calculators. So when it's multiplying the two numbers like that, it only divides by the first one and then multiplies by the second one. Foolish. So part C, all you have to do, I'm really asking what's the currents divided by the charge. That's basically all it's asking. So part C, all you're going to use is Ohm's law. So I'm just going to say E is equal to I times R. You know R that's 200, you know B that's 120, so then you just going to solve around that. And then, so it's asking for the number of electrons per second, and the current is just electrons per second. So it's just cool per second. Yes. You were just making a current.
Yeah.
So then just take the current divided by the charge of an electron. Is the projector getting louder, or is it always this loud? Okay. What these? Oh, right. So basically, the power loss is the same as the power supply. So the electric company then is supplying you a certain amount of power. So then what you want to do is take that power and then multiply by the amount of time in hours. So you got 24 hours per day, times 7 days a week, times 20 or 30 days. So multiply those together, that gives you a certain amount of energy. And you're going to take that and multiply by 15 cents.
So the power is already over, what's the person? Like time?
Is it for what?
Like, I'm just thinking it's like how the power is that like it's just person?
Well, that's per second. That's right.
Okay.
So that's right. So basically, yeah. So you have to turn. Right. So that's the power per second. So the energy per second. So that's just what we call the watts. So basically, you want to turn that now into kilowatts. So just divide by 1,000, and then multiply by the total time in hours that you're using for the light bulb, which is the 24 times 30. And then multiply that by 0.15 to get it into dollars. Still doing okay, Josh? How are we doing over here?
Have to explain that over
Okay.
there.
So we have 17 minutes. The 72 hours. And then how long it is in a month, so just 3600 seconds. Times 24 hours times 30 days.
Yeah, it should only be about $7 or $8. So that's the thing. Oh, you don't have to worry about the seconds. So, right. So we're just going to use the watts here. Right into kilowatts. So take that, divide by 1,000. Okay. And then, so everything you have here is right except for the seconds. So here are the seconds.
So we see.
Yes. Yeah. Because it's kilowatt hours. So we're just multiplying by the total number of hours, not total number of seconds.
We'll take out the 3600.
Good. So, $7.78. 76. Of course, it's a little more complicated, like charge you hookup fees and delivery fees and everything else. So what should have been $8 is now $100.
So do you think solar is a good deal if you live in Florida, or do you still think it's a rotten deal for the consumer?
Which one, the market price one?
Well, just solar power,
Oh, the solar power.
because you have to pay $15,000 to install it, or so, then you have to have it for 10, 20 years.
Right. In the long run, actually, one of our physics professors here, Dr. Scheller, he has solar power. So he did all the math for it. He said after about 10 years, it'll pay for itself, and then after that, you'll be getting money back from. Because basically, the other nice thing about solar power is the excess energy that you have, you can actually sell back to the power company, that way. So it's a good question.
I mean, in the end, it's not really a solar power plant
So, okay, so you
Not yet.
compared to like Florida where you got sunny days most of the time,
Right.
or California.
Arizona too. Those are nice places, but Arizona isn't too bad. Too bad. I definitely lived in places that were a lot grayer than what happens here. So, Buffalo, Cleveland, places like that, right by the lake. The entire winter it's just basically gray. There's almost never sunshine that comes through. And ultimately, solar power is the way to go. But the problems we have with that are how to transmit the energy from one location to another location, and then storage. So
Don't the solar cells deteriorate too?
they will, yeah. The main problems though are the transmission of the energy as well as the storage of the energy. Those are the main deficiencies. Get around those. Storage, well, the transmission wouldn't be too bad if we had room temperature superconductors. Superconductors is the best way to transmit energy, but most of them are super cooled, so they have to be down to a few degrees Kelvin for that to actually become superconductor. But that's really it. All right, good. So it sounds like everybody did well with those, so that's good. So now we're going to move on and start talking about more interesting things. Probably not finish the chapter today, but that's fine. We'll get most of it in. So far, what we've been talking about when it comes to current is what's known as DC or direct current. So this is what that means is when I connect a battery to a circuit, for example, the current only moves in one direction. That current moving in one direction is what we call direct current. Now, the problem with direct current is, for example, if I had my power company, or a power company makes energy, in that case, if I use direct current trying to transmit energy from the power company to, say, my house, or to USI, or to some other place, we have to use then transmission lines. So, as we know, transmission lines have resistance. Again, an ideal transmission line would have zero resistance, which is what I was basically just talking to Josh about, which would be something like your superconductor. But in reality, all of our transmission wires basically have resistance, which means when I'm trying to move the energy via currents, in this case direct currents, directly to, say, someplace like USI, I have a massive amount of power loss due to thermal energy. So as I'm having this current move through here, I'm radiating most of that energy away, which means by the time the energy gets to USI, around 90% of the energy has been lost due to thermal radiation. Not very efficient. So the way to get around this is to use a different type of current, which is what's known as alternating current, or for short, AC current. So what's AC current? So AC current is exactly what it sounds like, is that the directions of the current actually changes over time instead of being DC source, but the current always moves in one particular direction. What an AC does instead is that if I take an AC generator, for example, and connect that to a resistor, what happens in this case then is the direction of the current is constantly switching back and forth, typically in a sinusoidal type fashion. So the direction of the current is constantly changing direction. Now, this is actually the power that the power company makes. So what they actually make is they make a potential source where that potential source is actually an alternating potential source, which then creates an alternating current. And what that allows you to do is actually by a method that we're going to talk about later when we talk about magnetism, via induction, it allows you to increase the potential going through the wires, which actually minimizes the amount of power which is lost. So this is actually the benefit of using AC. So in AC, what you can do is you can use a transformer, where the point of the transformer is to take the AC power that your power company makes, which is relatively small, increase the size of it to thousands of volts, and then use the thousands of volts to transmit from one location to another location. In that case, it will actually minimize the amount of power loss. So in that case, if you're using AC currents, and this is my power company, and then this is USI, over that same transmission wire going from one location to another location, now you're only losing about 9% instead of 90%. So this is basically the usefulness of using alternating currents. So what you have in your house, or when I plug things into these power outlets, this is actually alternating currents, not direct currents. This is what's actually coming into your house. But again, your iPads or your computers and cell phones and things, those all use direct current. But when you charge them, you're actually using alternating current. It's kind of an interesting history with direct current and alternating currents. There was a big feud way back when with Nikola Tesla, who was a huge proponent of alternating currents, and Thomas Edison, who was a huge proponent of direct currents. The two hated each other and couldn't be in a room without getting in fistfights with each other. But anyways, Edison actually killed an elephant with AC currents to basically prove a point that AC current was dangerous because of the high voltages you could actually get. But it turns out at the end of the day, Tesla was right anyways, because we have to use AC current to actually move things from one location to another. But one thing you'll find about histories of scientists is they all basically hated each other and get in fistfights and tell each other they were dumb, and et cetera, et cetera. One of the worst was actually Niels Bohr. You should look him up at some time. He was a gigantic dick. But anyways, so history. So what is then AC currents? Okay, the way we actually create AC currents, and we'll talk more in depth about how this actually works later when we start getting into magnetism. But what your power company does is it creates actually a sinusoidal potential source, which means that if I was looking at the potential as a function of time, what you would find is this thing would actually go as a sine curve and basically do something like this, where this would go up to some maximum amount of potential, we call that V0, down to some minimum amount of potential, which is then negative V0, where V0 is what's known as the peak potential. Peak potential. So this is going to have some sort of time dependence as a sine curve. So in this case, the potential as a function of time then is going to be equal to that peak potential times sine of then the angular frequency times the time, which is then equal to the pardon me, peak potential times then sine of 2 pi times the frequency times the time. So basically, this is oscillating at some given particular frequency. Now, of course, every country has to be different, so every country uses a different type of frequency. So it turns out that in the US and Canada, we use a 60 hertz frequency, where basically the rest of the world uses a 50 hertz frequency. And because every country has to be different, we also use different potentials. So here in the US, for example, in the USA, our peak potential, actually our peak potential is about 170 volts. So this is our peak potential. And in places like Europe, they use a much higher peak potential. So if I remember right, it's about 340 volts is their peak potential. We'll talk about one of the consequences of that in a little bit. So Right. Using Ohm's law, what it says then is that what? We can then create a current that is also alternating due to the fact that, again, our potential is equal to the current times the resistance, which means that the current as a function of time is then equal to the potential divided by the resistance, which is then equal to the peak potential divided by the resistance times the sine of 2 pi times the frequency times the time. Which we usually define this would then be the peak current times then sine of 2 pi times the frequency times the time. So I0 here would be our peak current. So if I plotted my current as a function of time, and this is going to be a sinusoidal curve, something like this, or again, I'm going to have a maximum amount of current, I0, and then minimum amount of current minus I0. So what does this do for power lossage? So again, if I'm trying to transmit energy via a transmission wire, for example, in this case, we're going to have a power loss, or that power loss then, we now know is going to be equal to either the potential squared divided by the resistance, or equal to the current squared times the resistance. Either one of these is fine. So if I use the second quantity here, so this is going to be equal to then the peak current squared times the resistance times then sine squared of 2 pi times the frequency times the time. So this is my amount of power which is being lost. So if I plotted the power loss versus time, so what happens is when I square a sine curve, what happens is this becomes actually more sharply peaked. And since this is negative here, but when I square it, it has to become a positive, so I end up getting two bumps that look like. So if I plot this guy, I'm going to get something that looks more like this. And so this is my power loss. Now, because the frequencies are so high, for example, in the US again, that's 60 hertz, that means there are actually 60 oscillations in a particular second, which means that the average power here, or at least the power loss, is rapidly oscillating back and forth between 0 and a maximum amount of value, where again, the maximum value is simply equal to the peak frequency squared times the resistance. So since it's oscillating basically so quickly, what happens is we don't ever really measure it to be 0. We don't ever really measure it to be the maximum. We measure it to be an average value. So in this case, what happens is when we actually measure the power which is being lost, you're going to measure its average value. So it turns out that the average value of the power being lost is then simply equal to the average of the sine squared curve. So the average of the sine squared curve is actually this location here, which is simply 1/2. So the average of the sine squared is simply 1/2. So this then becomes equal to actually 1/2 of the peak potential squared times the resistance. So this is the average power which is being lost. So it's 1/2 of the maximum amount. So this is the average amount. Again, because this thing is oscillating basically so quickly, what you're going to measure then is the average location at which it is, which is actually 1/2 of the peak. So this term here, this is actually the root mean squared. So we can actually define this one to be the root mean squared. You guys remember root mean squared from 175? Talked about it when he did the velocity probably. So when you talk about root mean squared of the velocity, this was then equal to the velocity divided by the square root of 2. So that's all we're basically doing here. So here we're defining the root mean squared as then being the peak current divided by the square root of 2. Those are what's known as the RMS currents. Or if I use this definition instead, this would also then be equal to the RMS potential squared divided by the resistance, where the RMS potential is equal to the peak potential divided by the square root of 2. So it's what's known as the RMS of the root mean squared. So again, when I measure, or when somebody says that the amount of potential which is coming out of here is 120 volts, what they're actually quoting to you is the RMS value of the potential. Because again, the potential is actually oscillating, it's sinusoidally oscillating, so you're going to measure not its peak value, but actually what's known as the RMS value. So that means that in the US, the RMS value of our potential is 120 volts. This is in the USA. And then in Europe, the RMS value of the potential is equal to 240 volts. RMS in Europe. So, or using these, another way we can actually write then the average would then be equal to the RMS current times the RMS potential. So basically, anytime that I'm dealing with a sinusoidal source or an alternating potential with an alternating current, the power which is actually lost then is the current, RMS current times the RMS potential, or the RMS current squared times the resistance, or the RMS potential squared divided by the resistance. So RMS just means root mean squared, so it literally just means that RMS value is equal to the square root of the peak potential squared divided by 2. So this is actually technically means. Again, the benefit of this, and we'll talk more about how this actually works later, is when you're trying to send energy over transmission line, by increasing the potential to thousands of volts, you can actually then minimize the amount of energy which is being lost. So again, instead of losing 90% of the energy trying to transmit it from one location to another location, you're going to lose more like 9%, do much, much better. So you still lose a little bit, but at least most of it is retained, so you can actually then deliver energy to people as opposed to not much. So, good. So let's use all this and let's do an example. So, so this says calculate the resistance and peak current in a 1,000 watt hair dryer connected to a US line with 120 volts. So this is my favorite hair dryer. Connect that guy to find out what is the resistance and what is the peak current. Okay? So let's do this. So in this case, what do we know? So we know that this is the average power. So the average power in this case then is equal to 1,000 watts. So this is my average power. We know the potential. In this case, is our RMS potential, which is equal to 120 volts. And it's about 8. Good. So now, from this information, we then want to what? Determine what is the resistance, and also then what is the peak currents in this case. So to find the resistance, we can actually use the third definition down here of the power loss, because this is the average power. So in this case, we can say then the average power, which is the power loss, is then equal to the RMS potential squared divided by the resistance, which means the resistance then is equal to the RMS potential squared divided by the average power. So it's going to be 120 constant squared divided by 1,000, which then works out to be about 14.4 ohms. So this is the resistance inside of my resistor, which in this case is my favorite hair. I use it every day. Simultaneously, to find the current, we can actually use this one, from here, we can say then the RMS value of the current is then equal to the average power divided by the RMS value of the potential. But remember that the RMS current is the same thing as the peak current divided by the square root of 2. So this is then equal to the average power divided by the RMS value of the potential. So finally, get the peak current, all I have to do is multiply both sides by the square root of 2. So this tells me that the peak current then is the square root of 2 times the average power divided by the RMS value of the potential. So this is then equal to the square root of 2 times 1,000, all divided by 120. Like my numbers, what I run in this case then is I get 11.8 amps. Good. Now part B is then saying, okay, what happens if I take that same hairdryer, which has a maximum rate of 1,000 watts, and I now bring it to Europe and I connect it to a line where the RMS value of the potential is now 240 instead of 120. What happens to my hairdryer? Good. So in this case, the resistance here is dictated by the resistor inside of my hairdryer. So whether I have it here in the US or if I bring it to Britain or anywhere in Europe, that resistance is going to stay the same. What's going to be different then is what? Simply the peak potential here, which means if I want to know the power which is now being delivered to my favorite hairdryer, all I'm going to do is now take that 240 squared and divide by the amount of resistance that I have. Because the resistance, again, is dictated by the actual resistor. So let's use this definition. So this means that if we brought it to Europe, then the average power, which is going to be delivered to my hairdryer, is then going to be equal to the RMS value in Europe squared divided by my resistance. So it's going to be 240 squared divided by that same 14.4 ohms, which in this case works out to be about 4,000 watts. So this means that when I use my favorite hairdryer in the US and it's only getting 1,000 watts worth of energy per time, and then I bring it to the UK and I connect it there after putting my universal adapter, of course. They don't use the same plugs because everybody's got to be all different. And then I use it there, I'm now getting 4 times the amount of power delivered to my favorite hairdryer. 4 times the power. What's going to happen to my poor hairdryer? It's going to melt. This is what's going to happen. So, true story. This actually happened over the summer when I was in Tunisia. I was using not my favorite hairdryer. Fortunately, I don't actually have a favorite hairdryer, but I did have my hair clippers, and I got shaggy and hairy, and I couldn't stand myself anymore. So I started doing my hair with my hair clippers, and after maybe 2 minutes, it started smoking. Because the power was so high, and then eventually went and then died. So, but that prompted me to instead buy wireless one. So now when I go back at some point in the future, I'll bring my wireless one so I don't have to actually keep it plugged in the whole time and actually melt the poor thing. But yeah, so anyways, anytime you go to a different country, this is the point of using those universal adapters. So if you buy one of the cheap ones, all the universal adapter does is actually change the potential. Well, hypothetically, actually the cheap ones only change the plug. So when you plug in, it still keeps it at 240 volts, even though your stuff should only use 120 volts, which means if you touch your object that you're charging, it's going to get really hot really quickly because the power which is being delivered is on average going to be like 4 times the size. But if you buy one of the really, really expensive ones inside of there, they actually have a step down converter, which will actually convert from the 240 volts down to 120 volts. That way you actually don't melt your stuff. So in that case, it brings the amount of power back to where it's supposed to be instead of 4 times the size, so that way it doesn't actually melt anymore. But who has money to buy one of the expensive ones? Right? All right. Last topic. So we have one more topic to talk about in this class, has to do with what really happens inside of the wire. So as we talked about, what happens as the electrons move, they bounce around to different locations. So what really happens on the inside? What does the profile, how many electrons move in particular locations? That's known as the microscopic version of the current, or the current density. So we'll talk about that starting tomorrow.
I wrote that one first.
What's that?
I thought I wrote that one first.
Okay. Yep, I gotta stroll down to my office and grab the test anyways.